Hello, this is video 5 for section 2.3, and in this video we want to use inverse matrices to solve systems of linear equations. So you know how to use augmented matrices in row-reduced echelon form, but this is another way that we can use matrices to solve systems of linear equations. Let's look at what we have here. So it says, some systems of linear equations can be set up in such a way that inverse matrices can be used to solve the system. If we can set up a coefficient matrix A. So let's look down here. This matrix right here is the coefficient matrix A. All right, and this column represents all of the coefficients of X, the second column, all the coefficients of Y, and the third column, all the coefficients of Z. And you should be able to tell that because the coefficient of X right here is 1, and that corresponds with this 1 right here. And then as you move down, you'll see this coefficient is 2. So this element, ooh, that was interesting. I didn't know we could do that. This element here is 2. This element is 1, and that is because the coefficient on the third equation of X is 1. So when you set this up, notice I've got this on the left side of the equal sign. All my X's are in a column, all the Y's are in a column, and all the Z's are in a column. And that allows me to set up then this coefficient matrix. All right, so that's what this says. If we can set up a coefficient matrix A, and it must be square. It's got to be square because we're using inverse matrices to solve this. And in order to have an inverse, it must be a square matrix. We're going to take matrix A and we're going to multiply it by the variable matrix X. This here is the variable matrix X. It is what we call a column matrix. And let me clear up this screen a little bit for you. And we'll see how this is actually going to work and why it works in this fashion. Okay, so what we know is that, I'll just pull this one over here. When we do matrix multiplication, we always do the row times the column. So I'm going to do first row times this column matrix. So what would we get when I multiply this first row? I'm going to get 1x plus, move over and down, 1y plus 2z, and that has to equal the 1 that you see over here through matrix equality. And I'll talk about that here in a little bit. Look at the second row. 2 times x, move over and down, plus 3 times y, plus 2 times z is going to equal 2. So hopefully you can see through matrix multiplication how this system of linear equations over here can be set up using the coefficient matrix, the variable matrix, and then matrix B is the constant matrix, and that is the column matrix or the 3-by-1 matrix that represents all of these constants on the right side of the equal sign. So it is very important that you have your variables X, Y, and Z on the left side of the equal sign and all the constants on the right side so that you can set up this matrix equation. All right, what can happen here? So if we were to solve, let's just pretend like we were solving, I'll write this in purple over here. Let's just say that we were solving this equation, A times X is equal to B. All right, if A and B were real numbers, you would just divide by X. I'm sorry, divide by A, right? And you would divide by A because the multiplication and division are inverses. Okay, well, this is a little bit different when I'm using matrices instead of real numbers. So let me clear this up. And let's say that instead of real number A and B, let's say that now we have matrix A and B as we do here. Okay, well, I want to solve for this X right here, which means I need to multiply by A's inverse so that I can get this to be the identity matrix, or you can think of it as canceling out, going away, but really it's the identity matrix. Now, here's where this very important fact comes into play down here. The fact that matrix multiplication is non-commutative, so that means you can't multiply in any order. means that not only do you need to do the same operation on both sides of the matrix equation, so that means if I multiply by A inverse on the left side, I also need to multiply by A inverse on the left side, but you must also take care to do it on the same side. So that means that over here, I need to multiply on the left side of B. So X then is going to be A inverse times B, and you have to do it in this order, A inverse on the left side of B, because of this non-commutative nature of matrix multiplication. Okay, so let's look at example 5 here. For the given system of linear equations, set up and then solve the matrix equation AX equals B, where A is the square coefficient matrix, X is the variable matrix, and B is the constant matrix. This example is set up really nice for you. You've got your X's all lined up in a column on the left side of the equal sign, your Y's and your Z's. And then on the right side of the equal sign is all of your constants. So we can set this up. Matrix A is the coefficient matrix. So I'll write that right next to the system over here. So that's 2, 3, negative 2 going down the column here. And then it's negative 4, negative 6, 5. And then it's 6, 1, negative 2. So this right here is my matrix A. That is my coefficient matrix. The variable matrix, I'm going to multiply that by the column. It's a column matrix, or a 3 by 1. A matrix that only has one column, if you will. And that is my variable. So this would be X, Y, and Z. If my variables were, Q, R, and S, then that's what you would write there. So that is matrix X. And then this is going to equal my constant matrix, which in this case is 20, 22, and negative 18. That is my constant matrix B. So there's my equation. A times X is equal to B. To solve this using inverse matrices, we need to multiply by A inverse over here, which means I need to multiply on the left side of B. So this is going to tell me then that X is equal to, the variable matrix X is equal to the matrix A inverse times B. Okay, in a sense, this A inverse A, they cancel out, right? They make the identity matrix. So it's really just the identity times X. But you can think of it in terms of how you're used to solving equations. So let's look at this on the calculator now and see how we would do this product in the calculator. I did input the matrices in the calculator already. So if you look, let me see, let's look at matrix A. So matrix A I have as 2, negative 4, 6, 3, negative 6, 1, and negative 2, 5, negative 2. All right, matrix B I have inputted as the constant matrix. So if you don't have the matrices in your calculator yet, I would pause the video, get them in the calculator, and then press play again to come back with us to solve these. All right, so what we need to do to find the variable matrix is do matrix A inverse times matrix B. And that gives us this matrix. So 3, negative 2, 1 is matrix X, which means that to solve this system of linear equations, X is 3, Y is negative 2, and Z is 1. Now I want to show you just real quick what happens if you get it backwards and you do matrix B times matrix A inverse. So that error right there is a dimension mismatch. Dimension mismatch. Let's go back to our screen over here and see why this dimension mismatch would happen. I'll do this in black font here, or black color rather. Okay, so if we look at A, matrix A has dimensions 3 by 3. So that means that A inverse is also going to have dimensions 3 by 3. Matrix B has dimensions 3 by 1. So when I do A inverse times B, these two inside numbers are the same. So that means that my product matrix is going to be a 3 by 1, right? 3 rows by 1 column, and that makes sense. If, however, we do it the wrong way and we do B times A inverse, B is a 3 by 1, A is a 3 by 3, these inside numbers are not the same. So that means that this has a dimension mismatch. It means the dimensions of the columns in the first are not equal to the rows of the second. You can't do it. So that's what that means. It's just dimension mismatch means the product is not possible. Okay, that does it for video 5.